Welcome back to Very Ordinary Differential Equations. In this lecture, we continue studying second-order linear equations with constant coefficients and address the case of a characteristic polynomial that has a repeated root. So, we've already studied ay double prime plus by prime plus cy equals 0. But now we're going to suppose that this characteristic polynomial of ar squared plus br plus c has exactly one real root. How can that possibly happen when the characteristic polynomial factors as some constant times r minus r1 squared? Now there is a single real root of r1. Okay. Well then, you can show that e to the r1x is definitely a solution to the differential equation. But a fundamental set of solutions would need two different solutions, and e to the r1x is just one of them because we only found one root. That's all we have to go on so far. Well, what would the differential equation look like to generate such a characteristic polynomial? If the characteristic equation was a times r minus r1 squared equals 0, distributing that out, we get ar squared minus 2ar1r plus ar1 squared equals 0. That characteristic equation would have come from the differential equation ay double prime minus 2ar1y prime plus ar1 squared y equals 0. So the only way a homogeneous, linear, second-order differential equation with constant coefficients could have a characteristic polynomial with a single unique root is if it looks like this. Now, if I divide out by the non-zero constant a, we get y double prime minus 2r1y prime plus r1 squared times y is equal to 0. So in this scenario, we have found a single solution, e to the r1x, but we are still looking for another one. Now, with one solution having been found, e to the r1x, we need to find another solution to this differential equation. We just sort of make a guess that maybe a second solution looks like some function u times y1, where u is an unknown function. So this looks a lot like the variation of parameters technique. Well then, I can compute the first derivative and the second derivative by using the product rule. So if I assume that y2 is some unknown function times y1, then here would be the first and second derivatives. Now I take this y2 double prime, y2 prime, and y2, and I stick it back into the original differential equation at the top of the screen. And I get y2 double prime minus 2r1 y2 prime plus r1 squared times y2 should equal 0. So it looks like a big giant mess at this point. But we're going to manipulate this expression and solve for u. If I can solve for what the function u could be, then I just set y2 is u times y1, and I'll have found a second solution. As long as y is not a constant, then y2 is not a constant times y1, and they are linearly independent, and we're done. So we're solving this for u and hoping that u is not just a constant. All right, so here's the expression we need to solve for u, and we hope we don't just get a constant. I'm going to regroup terms according to what derivative of u they have. So here's the only term with u double prime. How many terms have a u prime? 2y1 prime, 2ry1. There they are. And how many terms just have a u? y1 double prime minus 2r1 y1 prime, and r1 squared y1, and there's that term there. But remember that y1 was e to the r1x. So in that last expression, we end up with y1 double prime minus 2r1 y1 prime plus r1 squared y1. And in this intermediate expression here, for y1 and y1 prime, we're going to go ahead and substitute the appropriate terms as well. And this looks awful, but it's about to get much, much nicer. Because inside this parenthesis, everything cancels. And inside this parenthesis, everything cancels. The fact that y1 was originally a solution to this differential equation makes this vanish, but also this term here happens to vanish as well. So having assumed that y1 is a solution to the original differential equation and setting y2 equals u times y1, we conclude that u double prime times e to the r1x must be 0. So we've reduced the entire problem of finding a second linearly independent solution to finding a non-constant function u that solves this differential equation. The exponential is never zero, so u double prime had better equal zero. How can I possibly find a single non-constant function whose second derivative is zero? We only need to find one. Okay, if I can just find a single solution here, then I can set y2 equals u y1, and I'll have found my second solution. As long as u isn't constant, then I'll have a linearly independent second solution. So can you think of a single non-constant function whose second derivative is zero? Well, the only functions whose second derivative is zero are linear functions, u of x equals mx plus b. Since we want it to not be a constant, we need that m to not be zero. And we only need a single solution. So what's the easiest non-constant linear function I can think of? U of x equals x. Overall, what do we have? If the original expression ay double prime plus by prime plus cy equals 0, if that gives you a characteristic equation that has a single repeated root of r1, then here's one possible solution to the differential equation, e to the r1x. But here's another one, x times e to the r1x. Both of those are going to solve the differential equation. The second is not a constant multiple of the first and is therefore linearly independent. You can also just compute the Wronskian and find that it's never zero. Therefore, if we have the situation where the characteristic polynomial has a single root r1, we conclude that a fundamental set of solutions is given by e to the r1x and x e to the r1x. Let's put these ideas into practice with an example. Find a fundamental set of solutions to y double prime plus 2y prime plus y equals 0. Well, the characteristic polynomial gives me r squared plus 2r plus 1 equals 0. What are the roots of this expression? Just negative 1. So we have a characteristic polynomial with a single root of minus 1. Since the characteristic polynomial has a repeated root, we apply our new technique and say a fundamental set of solutions is given by e to the r1x, e to the minus x, and x times that, x e to the minus x. So there is a fundamental set of solutions. So we may as well do a second example. Find a fundamental set of solutions to 4y double prime minus 24y prime plus 9y equals 0. The characteristic equation generated by this differential equation is 4r squared minus 24r plus 9 equals 0. Maybe we don't actually see how to factor this, in which case we might use the quadratic formula. Okay, so r must be 24 plus or minus the square root of 24 squared minus 4 times 4 times 9 over 8. But 24 squared minus 4 times 9 is exactly 0. So I have 24 plus or minus 0 over 8. So I have 3. The only solution is r equals 3. If there's only a single real root to our characteristic polynomial, a fundamental set of solutions is given by e to the rx and x e to the rx. So e to the 3x and x e to the 3x form a fundamental set of solutions to this differential equation. Third example, let's solve an initial value problem. 3y double prime minus 3y prime plus 3/4 y equals 0, with the knowledge that y of 0 is 3 and y prime of 0 is 1. Well, we begin with the characteristic equation 3r squared minus 3r plus 3/4 equals 0. Divide everything by 3 just for convenience. We get r squared minus r plus 1/4 equals 0. We can solve this with the quadratic formula, and we find that r is 1/2 is the only solution. We've determined that the characteristic polynomial has only a single real root, 1/2. Therefore, a fundamental set of solutions is given by e to the 1/2 x and x e to the 1/2 x. In other words, any possible solution must be some linear combination of those two things, a constant times e to the 1/2 x plus another constant times x e to the 1/2 x. We can compute the derivative of this. Y prime is c1 over 2 times e to the 1/2 x plus c2 e to the 1/2 x plus c2 over 2 times x e to the 1/2 x. So we know our general form of our solution and we've computed its derivative, and now we can start using our initial values. Taking y of 0 equals 3 into the first expression gives me a 3 on this side because y of 0 is 3, but plugging in x equals 0 makes this term vanish entirely and leaves just behind a c1. So right away we see that c1 must equal 3. Taking y prime of 0 equals 1 into this second equation, we get 1 is y prime of 0. This exponential becomes 1, this exponential becomes 1, and this has an x out in front of it, so it vanishes altogether. Therefore, c1 over 2 plus c2 must equal 1. And since we already know the value of c1 must be 3, that immediately lets us solve for c2 is negative 1/2. Now that we know the two constants, c1 is 3 and c2 is minus 1/2, we have found the exact solution. Y must be 3e to the 1/2 x minus 1/2 times x e to the 1/2 x. What have we learned? If we have a second-order homogeneous linear differential equation with constant coefficients, ay double prime plus by prime plus cy equals 0, we know we need to solve the characteristic equation ar squared plus br plus c equals 0. If there are two different real roots, we've already seen that a fundamental set of solutions is given by e to the r1x, e to the r2x, where those are the two distinct real roots. But today we established if there's a single real root r, then the fundamental set of solutions is given by e to the rx and x e to the rx. This still leaves behind the question, however, of what if the characteristic polynomial doesn't have any real roots at all?